Alright, so this video is going to be on energy diagrams. And so energy diagrams are schematic representations of the energy changes that take place as the reactant moves to the products. And this will help you determine how readily it may occur, how many steps are involved, as well as the relative energies of reactants and the products and intermediates, which we will see later. Okay, so we have an example of an energy diagram here. And then y-axis, we have the energy. And in the x-axis we have reaction coordinate. And this is basically just the reaction progress as we go from left to right. So we have compound AB plus C with a negative charge on there, and then we end up with the products on the right with B bound to C, and then A is now by itself as an anion. Okay, so let's go ahead and kind of point some things out, some key features of an energy diagram. This kind of the reactant energies, initial energy, and the products and final energy is delta H. Now, from the energy of the reactants to the highest point, that is called the activation energy or energy of activation. And this is almost like the barrier that is the energy that's required in order for this reaction to occur. Okay, so you can think of it as like literally walking over a hill. It takes a lot of effort to get to that top of the hill, and then eventually it's just downhill. Okay, that top of that hill is the transition state indicated by a double dagger, and this is, again, it's called the transition state, and it cannot be isolated. So you can isolate reactants, products, even intermediates, but you can't isolate transition states. Okay. Now, what does a transition state look like? Well, as you see, we have compound AB combining with C and then losing A, right? So essentially what we have is, at some point we have to have a state or a transition state where A is partially bound to B and also B is partially bound to C. Okay, so A is on its way out and C is on its way in. And that gives A delta negative charge and C a delta negative charge as well. Because A will become completely negative eventually, and C used to be negative. Okay, and that's pretty much the transition state. It's like what's happening in between. Now let's take a look at essentially four different possibilities for energy diagrams. So I'm going to draw the x-axis and the y-axis and just copy and paste these four graphs essentially. And so what we're going to end up doing is giving you these four different scenarios, and you're going to need to know these four different scenarios. Okay, so we'll have a large activation energy, and then we'll have a positive delta H for this first one. So what does that look like? Well, it looks like this. If it's positive H, that means we have an increase in energy, right? And that delta H, if it's positive, means it's an endothermic reaction. Okay? And that's because we had to put energy into the system in order for that to climb that hill, right? That hill is the activation energy. If it's really big, that means that's going to be a slow reaction. Okay, very key points here. Okay, so this particular graph, what does this represent? Well, that's going to represent a large activation energy again, as well as or not as well as, but a negative delta H, or a negative enthalpy. Okay, and here's the enthalpy. Here is the activation energy. Okay, so when we do have a negative value for delta H, that is going to be an exothermic reaction. So it's kind of ambiguous, right? Like, what's a large activation energy? What's a low? So here's a low activation energy. It's kind of obviously small, right? And so here we have the delta H for this particular reaction, and this is endothermic again because it's positive. And here's the itty bitty activation energy. Okay, if it's a small activation energy, that means it's fast. Okay, it's a small hill, right? It's essentially just a curb. If you want to think of it that way, you can climb a curb really easy. So here's another scenario This is an exothermic reaction with a small activation energy. So low activation energy, again, equals fast. And then that exothermic reaction means we have a negative delta H. And that's all she wrote for these. There's 4 different scenarios. You need to make sure that you understand all features of them. All right, so what time is it? I think we should have a conversation. We should talk about practice, y'all. All right, so let's get some practice in real quick. This stuff, I think, is pretty easy. So we'll try and move quickly on it. But what we want to do is draw an energy diagram, and we want to have a couple features applied to that. So products are higher in energy than the reactants. Activation energy is large, and we want to label all of the following. So we're going to have, we have to label the axes, the starting material, SM, the products, TS is the transition state, delta H is enthalpy, and EA is activation energy. All right, so go ahead and pause the video and try that on your own first, see if it matches mine. So products are higher in energy is what you want to start with, right? Other than the reaction coordinate and energy. So what does it mean products are higher in energy? Well, just draw the reactants and then draw the products. And you can put the products, basically the line has to be anywhere above the reactants energy. And so that's pretty easy, right? We want a large activation energy. So just draw a big curve going from the bottom to the top, okay? And that is going to be the activation energy here. So obviously there could be not infinite possibilities, but there's going to be lots of possibility. The best bet is to make it obvious. And so here's our delta H. We have all of those labeled, activation energy, and then transition state. So our transition state, again, is the top of that mountain, right? So let me fix that arrow real quick, make it more obvious where it is. The top of that mountain is the transition state. That's when the reactants are partially forming the products. So it's like some combination of both. And that's it for that particular reaction. So let's try another one. Drawing an actual transition state. So here's this compound on the left. We form a carbocation and water. So we've removed water from this, right? So the only thing that changed is we broke a carbon-oxygen bond. That bond is broken. And so we want to draw something that's somewhere in between. So we'll draw a bracket. And we'll draw a dotted line representing that partial bond that's there. Whoops, not a full positive, but a partial positive. And a partial positive on the carbon as well. Because remember that oxygen is completely positive on the left, and then the carbon is completely positive on the right. So the transition state represents somewhere in between. So they're both partially positive because, that's the charge that's involved in this particular reaction, okay? So it's on its way to being positive and was positive. So draw somewhere in between, delta. All right, let's try another example. We've got another energy diagram. Y-axis is energy, x-axis is the reaction coordinate, which is just the reaction progress, right? Going from left to right. So let's say we've got this one here in red, and we've got A, D, and C points on this particular graph. And then we've got another one in blue, another curve. So let's see here. All right. Now we've got E and B for the top of the mountain, and then the products on that one. So what do we want to do? We want to label. We want to identify if these reactions, red or blue, are endo or exo. Which one of these two is faster? Which has the lower energy for the products? All right, and let's see, what else do we want? We want to determine where the transition state is, as well as label the activation energy, and then label enthalpy, delta H. Okay, so pause it, try it on your own, and then we'll run it back real quick. Endo or exo. Okay, so C has a lower energy than A, so that's exo. B has a higher energy than A, so that's endo. All right, which is faster? So remember, this is all about activation energy. They both start at A, point A, and D is lower in energy than E, which is that top of that hill. So reaction A to C is going to be the faster reaction, which is lower energy products. Well, C, right? So that means the A to C is the lower energy products. Where is the transition state? Well, that's B point D and E. Label the activation energy. So that's going to be where the reactants start, to the top of the mountain. And that's here and here. Okay. Now label delta H. We also remember it's just basically the lower energy points on those, and that's for the red reaction. And now we want to draw for the blue, which is right here. So we have two different delta H's here. Okay, and that's it for this particular problem. So let's take a look at another type of reaction diagram, and that's a two-step reaction. Okay, so basically, if a reaction occurs in more than one step, then that means that the reactant, or that means that there needs to exist a species that is neither the reactants nor the products. Okay, so it must involve a species that is neither the reactants or the products. Nor the reactants. Boom. All right, cool. So what does that look like? Well, what is that called? Sorry, that's called an intermediate. Sometimes called a reaction intermediate, or just the intermediate, or a reactive intermediate. Either way, it's an intermediate. So we've seen this before. We have an alkene. Let me move this real quick. We got more room to label things. We have an alkene reacting with HBr, labeled in blue. We attack and then kick the electrons to the bromine, and now we've got a new product, right? Well, that's a carbocation, and there's that blue hydrogen to keep track of it. We got that bromide ion because it was heterolytic cleavage for that bond breakage. This is an intermediate, and it is, I don't know why I labeled transition state, my bad. It's just a reactive intermediate, or a reaction intermediate. And so this particular carbocation it's not the desired product, and it's not a reactant. It's just something in between. And that bromine, or bromide, can now attack the carbocation because the bromide is a nucleophile, the carbocation is an electrophile. Bada bing, bada boom, bring it together, you get the new product on the far right with the H and the Br added to that. So this is an addition reaction broken down into two steps. So what does that look like on an energy diagram? Okay. Looks like, silly Willy. My iPad likes to do crazy things. All right, so we've got the alkene right here as a reactant with the HBr, and then our intermediate is basically the middle trough. So it's still high in energy because it is a reactive intermediate, and that is here, and that is the carbocation intermediate. Okay. Now, we obviously have our products on the far right, and then we have two different transition states here. So we got transition state 1 on the left, and then we got transition state 2 on the right. Okay. We'll also have two activation energies and two enthalpies as well. So let's go ahead and label those for you. So remember that the activation energy is basically from the bottom of the hill to the top of the hill. So there's activation energy number 1, and then we have the trough, that's the bottom of one of the hills, and then we have the top of that hill, that's activation energy number 2. Okay, so this difference in energy between the trough and the lower reactant energy is delta H number 1, and then the trough to the products, that energy difference is delta H number 2. All right, so the last feature is we want to mention or first of all, we already know this is a two-step process, but here's step 1, here's step 2, and this is important to note because it leads us to our last vocabulary word essentially, or term. And so that is the rate determining step. So if we have a multi-step mechanism, then the one with the higher activation energy is called the rate determining step. Okay, and so that's it's kind of like a bottleneck. If you have the higher activation energy, that means it's the slowest step, and therefore that's kind of going to dictate how long the reaction takes as a whole, okay? AKA the rate determining step. And that's pretty much it for this one, and let me know if you have any questions.